Hello, ladies and gentlemen. Welcome back to GGS300, Quantitative Methods for Spatial Science. Today we're going to be going over the 6th lecture, which is going to be on sampling. Just before we begin though, what I wanted to do was to actually just give you a little bit of a brief overview as to where we're at within the course. So essentially now we've done all of that first section of the course, and we've basically been through all of the labs for that portion. You've had all of the assignments set. So essentially what we're doing this week is we're going to actually be doing the testing. So you have that set of ungraded tests, which are basically essential for you to take before you take the midterm exam, because you're going to realise what you do or you don't know. And then obviously you've got the midterm exam due the same week, which I'm sure you're all busily revising for. Okay, fantastic. Let me know if you've got any other questions. I've been speaking to some of you via email. That's great. It's good to reach out with you and go over anything that you're stuck on. This week, obviously, we're going over Introduction to Data Sampling. So, as I said, we've kind of gone from that first part of the syllabus where we focused on descriptive statistics, and now we're moving into that third of the syllabus where we're focusing on inferential statistics. Okay, so in the descriptive statistics part, we were providing numerical or quantitative descriptions for the distributional characteristics of geographic data, for example. Whereas in this part now, what we're going to be doing is we're going to try to make generalizations about statistical populations based on information that you or I may go out and actually gather from a population. Okay, so just remember that the population is essentially the total number of entities that we've got within a boundary area of study that we may decide that we want to go out and sample. So maybe if we want to look at house prices in Fairfax, the boundary would therefore be Fairfax, or if we're going to carry out a census of the United States, then our boundary for that population would be the entire population of the United States. And then that actually contrasts with a sample that we then may have. So essentially a sample is where we have a particular subset of a population that we then select in order to try and obtain metrics which can be generalized to an entire population. Okay, so these two definitions are really important for what we're now going to cover within today's lecture, because they really inform how we're then going to start to try and design sampling strategies in order to understand information about a wider population. So then just going back to that spatial scientific process diagram, which I've presented already previously within the course this year, so this semester. And essentially what we have within that process of carrying out spatial science is we have generally kind of more descriptive approaches on the left-hand side there, so where we might identify a problem, and then we might go out and collect and prepare data, process in terms of descriptive metrics, which we've covered, so the mean, the minimum, the maximum, the range, the standard deviation, the coefficient of variation, these types of metrics that we've been focusing on, and then we may use them to draw conclusions, potentially formulate hypotheses. And that's the descriptive approach. And then that contrasts with now what we're moving on to, which is where we may formulate formal hypotheses about the way that we think the world works. And then we basically go out and we might collect data, we might have to then prepare that sample data in order for us then to test these formal hypotheses that we have. And when I say formal, I mean that we may expect that the world works in this particular way. And if our data doesn't show that, then we would fall back on the complement of that particular way, which maybe suggests that there's no evidence between a relationship that we've seen. And I will get more into how we phrase that and how we approach this hypothesis testing, this formal hypothesis testing, next week as we start to move into the actual tests. And obviously in that process, once we've undertaken that formal hypothesis testing, we would then have to evaluate the hypotheses that we've made, and then we either go back and we redefine the model and the theory, or hopefully, ideally, in a better way. I mean, I'm sure we will do that refining part, but in a better sense, I hope that we can actually draw conclusions from the work that we've done and actually use that to make the world a better place. So whether that's to inform governmental decisions, or whether that's to inform business decisions, or decisions about how you and I may decide to live our lives, This is all where the real kind of magic happens. And there are some academics who specifically love that kind of developing the model and redefining the theory part. Fine, great, we all like that. But really, the bit that kind of gets people out of the bed in the morning, at least the way I see it, is to actually have a better impact on the world. And you can really do that by using the types of methods which I'm teaching you within this course, because whether you like it or not, the world works on quantitative information, and that's not going to change. I see the value in qualitative methods, but at the same time, quantitative methods have also given us the electricity system or the internet. That the fundamental math that informs how we design those systems and operate the systems has fundamentally made the world a better place. Okay, so I don't want to get too bogged down in this, and each week I will return back to this. So by the end of the course, you definitely will have a very strong understanding of how we do quantitative approaches for spatial scientific science. Okay. So what's the aim of sampling? Because that's obviously the purpose of this lecture today. Well, what we want to do is we want to make an inference about an entire population that we're interested in. Okay, so we need to make sure that the sample that we collect, therefore, is actually representative of that entire population. And quality matters. Quality is something which you should always be concerned about in your sampling approaches. There was advice given to me when I was starting out in the field of research and getting anxious about doing a PhD viva, and the person told me, as long as your methods are correct and the methods of inquiry that you've used have been designed appropriately, so you focused on high quality methods and adhering to best scientific methodological standards, then whatever the conclusions of your PhD, even if your examiners or the people examining the work disagree with you, or even just other academics when you publish a paper, as long as the methods are sound, then you'll be in a really strong place. So you need to put a really high focus on making sure that you focus on quality, how you carry out rigorous statistical analysis based on best practice. And then you'll be in a really strong place. So I think the same goes for your performance within this course. Focus on quality, focus on how you actually carry out these tests, focusing on the main assumptions, which I'll repeatedly state in each of one of these lectures, and which then will demonstrate when we get into the actual lab work. And when I say assumptions, that's because these are the requirements in order for each of the tests to be carried out. And if you jeopardize those, then that's a serious issue. You can't rely on the results. So it relates to this key point, which is that the quality of the sample particularly determines the quality of the analysis. So it's a good example. So why do we need sampling? Well, necessity. So if we want to, we are unable to go out and carry out a census of all businesses within the United States, but we do need up-to-date jobs information, labour market statistics. So the astute of you will have noticed that yesterday we had very good news coming out of the US for jobs growth, which is going to help the recovery post-COVID, which is great. But obviously we can't go out and sample every single business when we do that. So the Bureau of Labour Statistics will use survey methods to survey a representative number of companies in order to understand exactly how their businesses are adapting for changing conditions, how many redundancies maybe they've made in the past quarter of the year, in the past period, how many people they're expecting to recruit in the next quarter of a year. These types of statistics, and they basically feed forward into our expectations for the future. And even those statistics which are made based on survey data, you'll notice occasionally they're actually revised at a later date as more information comes in. But the very principle of this is that essentially we're using a sample to basically generalize characteristics from that subset of entities that we've reached out to, in this case maybe businesses, to generalize to a whole population, which in this case may be the United States economy. Why do we do this? Well, efficiency and cost effectiveness. So as I said before, necessity drives us into needing to actually just sample a certain number of businesses rather than the entire economy. And why do we need to do this? Well, for cost effectiveness, for example. So whenever I talk in this about the trade-off of sample size, a lot of the time this is going to be in terms of effort, and that's also going to come down, but essentially to cost. As someone who's been trained in economics traditionally, I'm always going to reduce everything down to cost because that's the way that I view the world. But ultimately, if you have more hours that need to be spent, that means you need more people to do that, and generally that means that there's always a cost incurred somewhere. Even if that time is free from those people who are carrying out the sampling, there's an opportunity cost for them doing that one activity rather than doing something else. So I'm always going to view this as a cost effectiveness trade-off. We, through doing this process of sampling, if it's designed correctly, can actually achieve very high accuracy, and that's a fantastic thing. And I'll show you today how we do that. And actually, the people who design those surveys, whether at the Bureau of Labor Statistics or whether working on US census data, obviously we don't census every year, and in between then they often carry out survey information in order to update forecasts of population, for example. So essentially, they are very highly trained people who are designing these surveys and sample design experiments, and you can achieve very high accuracy if you're able to control for all of those characteristics which introduce bias into your data. Repeatability of the data collection, so yes, that's something which you're able to do. Generally, there's software available these days which can help you actually reduce the burden on you. So if you're carrying out a survey, maybe you're able to automate a lot of that survey information. Maybe you don't even use paper surveys anymore. Maybe you send them out electronically, which obviously I would always preference. But if you're trying to get a CEO of a major company to respond to you, a letter actually works fairly effectively rather than a blanket email. But these are great ways in order to basically try and obtain information, and you can repeat this collection very frequently once you've got the protocols and the operations set up. Can provide a lot of detail through in-depth methods. So I've spoken about this before, kind of the sample size and how that affects the actual cost of carrying out the activity. So there's a trade-off there, right? So there's going to be a width versus depth trade-off as just one example. That's going to relate a lot to those methodological approaches which I discussed earlier within the course when we were focusing on qualitative versus quantitative methods. So quantitative methods are going to provide you with that great width across all of your sample population, for example. And that's going to allow you to systematically understand things about the world and draw general conclusions, whereas your qualitative methods are going to give you a very, very large amount of detail, and you're going to go very, very deep into maybe just a few entities that you've drawn in your sample, but it's not going to be as representative, so you're going to have less breadth in comparison, but you're going to have an awful lot of detail just on those few individuals or entities that you've ended up doing that qualitative work with. So this is something which comes down to researcher preference. It's also being driven by the research question which you're investigating. So what's the goal of sampling? Basically, you need to derive a truly representative set of values from that sample, which hopefully reflects the population, and therefore you need to actually control for the characteristics within the population in order to, I would prefer to say, minimize bias. So here I say without bias, I mean yes, but it's really a minimization process of the degree of bias within your sample. So that's our aim, that's what we want to do. We want to minimize the potential bias so that we get the most truthful representation of the overall population possible. So sample design. This is the process essentially where we actually decide who we're going to select. The procedure used to select individuals, I would rather say. So the sample design, we might decide the method for how we select those individuals in this process, and I'm going to give you a few examples as to how different some of those methods can be in the next few slides. We want to get a high degree of sampling accuracy, in which case we need to have a proper sampling framework with a strong sampling design. and we need to have an appropriate number of samples, so a decent size sample size in order to minimize bias. So these are things which we're going to work through here. I'm going to give you an example of how we would do this in practice, and you need to make sure that you read the content within the book, and I think that will place you in a strong on a strong trajectory in order to really understand this topic and then grasp the methods which are going to be coming at you in the next few weeks, which will focus on inferential testing, and which therefore will be based on data predominantly collected via sampling. So the goal is to get the relationship right between accuracy, cost, and sample size, so that trilemma of trade-offs which you're going to have to balance out when you're starting to focus on a research area. Okay, so imagine in all of this that you've been set a research project, and I'm tasking you with going out and collecting the sample. These are all the things that you need to consider when you're actually designing that research project. I'm very sad, sampling accuracy keeps me up at night, and I'm just giving you an example of a paper which I mentioned before, which we carried out last year, which essentially focused on trying to sample Wi-Fi access points in central London and other places, so that we could then start to build a predictive model for the number of Wi-Fi access points in relation to building density. If you get the sampling wrong in this case, then the information you have about the population is wrong, and then your predictive model is essentially wrong. So it's really important that you get this correct. I don't really like this this graph here. It came out of the book, but I'm including it because it is kind of relevant. The reason why I don't like it is I don't like two axes being put on the same graph. This is kind of personal preference whether you do this or not. Generally, I think it's less clear, but I mean, people do it. It's the same kind of contentious issue as putting 3 dimensions on a graph as well, whether you want to get into that or not. I mean, generally, it's not a practice which I do. It's more eye candy. So anyway, let's just go over why we have this graph here. So it's trying to emphasize the trade-offs essentially in the sample size. So if you look at the A line here, which relates to the y-axis with the A label, you'll see that this relates to the level of imprecision within the sample. And then on the B-axis, essentially we have a curve here, and that relates to the amount of effort that you might have to put in to actually collect your sample, okay? And then on the x-axis, we have the sample size. So on the left-hand side, we have small sample size, and the right-hand side, we have a large sample size. So if we now just go to what would happen if we had a small sample size, so essentially if we had, if that was the case, we'd be on the left-hand side of the graph. And if we look at the A-axis, for that A line, it's very high, so we'd have a high amount of imprecision. And then if we look at the B-axis, we'd have a very small amount of effort. So you see how it's a trade-off. If we then look at whether it's a large sample, we would essentially have a low amount of imprecision, but we'd have a high amount of effort that is actually required in order to obtain the information that we want, okay? So we could be anywhere across this range. What we want is really the smallest sample size, which provides us with the most amount of precision in our sampling technique, okay? And this is quite hard to get right, but there are methods which enable us to do this. There are tools that you can use to calculate your sample size based on the overall population and the degree of reliability that you actually want on your sampling process. And on the right-hand side here, you'll just remember that example which I gave you in the probability lecture previously, where we were calculating the relative frequency for actually flicking a coin and basically getting a heads rather than a tails based on the number of coin tosses. So if we look at the number of coin tosses, n, this is the sample. If we look at the frequency, number of heads, this is the number of times that heads occurred, and then we get the relative frequency, which can be interpreted as a probability on the right-hand side there. And if we look at the first one, where we've got very small amount of effort required, we're only taking 10 sample points, then actually we end up with 8 heads, which would indicatively tell us that there would be a 0.8 probability, so an 80% probability that the next time we flip the coin, it would be heads, which instinctively, a priori, because we know that flipping a coin is 50-50, this is wrong, okay? And that's wrong because we've only had a very small number of sampling points. But then if we look at the flip side, if we go to the very bottom of that table and we look at the most accurate prediction that we've got, we're actually tossing that coin 20,000 times, okay, and we're getting 10,038 heads, and that would give us a relative frequency for heads, which is 0.5019, so 50.19% chance that the next time we flip the coin is actually a heads. So this gives you an example of how you increase the sample size hugely, but you get a far more robust result. The level of precision in your results is hugely improved. And I guess my question to you is, you know, it's one thing for us to go out and just collect data and collect sample data, and you might want to cut some corners to improve the efficiency. But let's just think of it this way. If we were sat in Manhattan, we had an investment firm, and we were making an investment based on some analysis that we'd actually carried out, then where would you want to put your money? Would you want to invest based on the answer that you got from the minimal sampling evidence that was collected, or would you want to put your money based on the investment advice that you picked up from the survey based on the much larger one, which gave you a much more precise probability? And the likelihood is that you want to go for the second one because you've got a much smaller amount of imprecision. Okay, so this just gives you an example of why this matters, and how actually in the real world there's huge implications for the level of reliability that you have within your sample. Sampling design. Okay, so now we're going to focus on exactly the types of methods that are involved in sampling design. And there are different procedures in order to carry this out. Okay, so we're going to start with these first 2 points that I'm going to go through, and then we're going to go all the way through to the final remaining ones as well. So firstly, what we want to do is we actually want to define the target population. So essentially this is all those individuals that we actually want to study. So for example, if I told you we wanted to go out and actually derive the potential property prices in Fairfax, the city of Fairfax, then your target population is going to be all of those real estate buildings, either houses or commercial, that exist within the Fairfax city boundary. Okay, so this is how we would define the target population. Geographically, that's really easy, but then it becomes more complicated if you're not delineating by geography. For example, in some of the work that I did for my PhD, I was delineating based on the industrial sector, and then also the firm size that we might specifically want to target, and therefore that's going to change the dynamic for how you actually set your target population. It might be based on a whole economy, or it might be based on a regional economy, depending on the type of approach that you're taking. So, you know, I'm talking from an economic geography perspective here when I'm talking about how we define these populations, and this is kind of a very standard way for us to go out and collect this type of information. We then want to define a sampling population within that sampling frame. So the sampling frame essentially is the structure that contains the set of elements that we want to go out and sample. So it's the list of individuals that meet our demographic characteristics that we might want to sample, or maybe it's the boundary line around the city of Fairfax that delineates exactly the area that we want to sample. So that's the frame, the total set of elements that could be potentially called upon in our sampling approach. The sampled population is essentially all entities within the sampling frame that could potentially be sampled, and the sampled area is just all those locations within the frame from which the sample could be drawn. Okay. So then we move on to how we actually select a proper sampling design. For most of what we're doing here, I'm going to be talking about probability-based sampling design, and that's because this is the standard quantitative way for us to actually get the sample data that we require. So as we move into the inferential hypothesis testing based statistical approaches, then there's an assumption that the data have been collected from a random, so you have a random sample, as I'll explain later, and therefore this is kind of a fairly one of the most common approaches for actually sampling areas. Okay, you could use a non-probability based sampling design. So, for example, I was speaking about some of the work which I did previously. So this was my PhD thesis, and within there, most of it was quantitative research that I actually carried out. But I did do just a very small amount of qualitative work in there, and that was to kind of supplement the more systematic quantitative work that I did. And I actually used a non-probability based sampling design within that. So I was looking at high-tech firms. I was looking at those firms which particularly use the most cutting-edge digital technologies, so machine learning, software engineering, data analytics, those types of activities, because they're particularly sensitive to the thing that I was focusing on, which was broadband infrastructure and how that affects firm operations, growth, productivity. And as a consequence, I was focusing on a very small subset of firms, so just kind of digital economy, high-tech firms, and I was focusing on just the very, very small ones because they've got resource limits, essentially. So by the time I had that type of criteria predefined, it meant that I was essentially needing to go out and actually select firms which met those criteria. So it wasn't necessarily the best approach for me to just use a probability-based sampling design. So I was actually just trying to do case studies with firms that met those criteria, and therefore there was a degree of subjectivity involved with who would actually speak to me and whether I wanted to include them in my sample or not. But it was kind of based on those set of criteria that I wanted from the very start of how I designed my case study based approach, which was based on firm size and sector. Okay, so they are the two main probability or non-probability based sampling designs. I'm going to focus mainly within the rest of this course on probability based sampling design. Then once we've decided that, what we need to do is we actually need to prepare the research instrument and operational plan. So let's say we're doing a probability based design. I'm sending you out to go and carry out a survey. We need to make sure that our measurement instrument is appropriate for what we're trying to do within the research question. We need to make sure as well that we've actually tested that instrument to make sure that it works. Hopefully we've chosen that instrument because that's a fairly common way to actually carry out this type of activity within the existing literature, so we're building on that past scientific knowledge. And this instrument could be a wide variety of things. It could be surveys, field measurements, or just pure observation, it could be interviews, whatever. But essentially we need to make sure that we have a scientific way to actually reproduce the use of that instrument. So here I'm particularly talking about those field measures or survey designs, which we can standardize and reuse in a scientific way. Point 5, as I've already mentioned, we need to make sure that we've tested that approach to make sure that it is doing what we think it's actually doing. So is the instrument efficient? Is the instrument working? And if it's not, we need to be prepared to actually revise the sampling plan. Okay, so maybe if you've designed a survey, what you need to do is you want to test it out on a few people beforehand, a few people from that desired sample that you want to obtain. I mean, there's a good example. So I've been reading about the vaccine strategies in various countries and how effective some of them actually are. And Germany actually introduced two-factor authentication for anyone to actually book an appointment to go and get a vaccine. But obviously those people who are eligible, at least in Germany right now, to actually go and get their COVID vaccine are pretty much all over 80. So actually confronting your octogenarian Participants with a two-factor authentication code obviously is going to confuse many people. They're going to struggle to get through that process before they even are able to sign up for something. And that's the type of example that you don't want to have something like that within your survey, okay? Maybe you're, just one example, maybe you're interested in surveying people's attitudes to why they don't use the internet for certain things, then deciding to do an e-survey and send out that method via email is obviously going to be a biased approach, because you're going to miss most of those people who aren't using the internet, okay? So this sounds really obvious, these examples that I'm giving you of why things are going to fail, but the likelihood is that there's going to be things which you just don't realize, and therefore you need to make sure that you test them. I think that one of the biggest issues with survey design is the actual interpretation of the question, whether you're using plain language, plain English, or whatever language, whichever language you're using to survey your target population, that it's actually in plain language that's understandable to the participants. And that's another reason why you need to make sure you test this in advance. Academics, particularly people who are working at close on a research problem, are really bad at seeing this from a kind of outsider's perspective. Whenever I do outreach for any work that I've done that's going to go out to the media, basically to emphasize maybe some important conclusions that were found or the ramifications, maybe for global government decision making or whatever, I usually just palm off the research entirely to someone from the PR field and just ask them to kind of decrypt whatever I've written in the potential press statement, because I just feel like I'm not really geared up myself to kind of put that in kind of plain language yet for people to kind of interpret, because it's quite hard to work out what is and isn't understandable to other people from outside your field. So you need to recognize that as a limitation and just rely on other people's intuitions. You need to make sure you get the survey out there to show people, and quickly and early on in the design process, so that you've got time to revise it. And then you go out and you collect the samples. Okay, so we've been through these 6 different steps. It's important to be aware of them, particularly if you're going to go out and you're going to do a dissertation. Then just make sure you are aware that this is the proper way in order to actually design a sampling procedure. So non-probability sampling designs, as I've already said, this could be qualitative work, it could be case study interviews. How do you actually obtain the sample for that based on non-probability approaches? Well, you could do convenience sampling. So here it's person on the street. Maybe you want to survey people in the town centre. So you go downtown and you want to ask people about their perceptions on parking near the downtown area, and perhaps get their input on how they feel about public transit. Well, then maybe in that case, convenience sampling is okay, providing you get a large enough sample and then you collect their key characteristics in order for you to later to control for bias in the sample. But I think you need to kind of be careful about this convenience-based approach, because it's very easy to bias your sample. It's not as easy as other approaches that you may have at your disposal. Targeted sampling. Well, I've already spoken to you about this, about the previous work that I've done. So maybe you want to speak to a particular person, a particular group, a market, a company. So maybe you want to go out and you want to understand the attitudes of people working within the oil and gas industries in relation to their feelings about clean energy policies, which, in essence, are going to have a very negative impact on their business model. And you want to gather opinions from them, in which case then you would basically need to make sure that you're actually getting those correct people within that correct industry. Okay. So I think I've spoken about most of the different types of targeted purposive sampling approaches that you could have. So expert sampling, so subject matter experts, is also another very useful thing to do. I mean, that's pretty common in the risk analysis field when you just don't have scientific data to model all of the threats that you need. Heterogeneity sampling, so looking at a range of ideas, not just the average. Okay, that's fine. Snowball sampling, so that's where you may use one participant that you've obtained to then help you find more participants. Maybe you're interested in percolating through a social network, in which case then you might find that a snowball sampling approach is the best for you. Okay, but you just need to recognize the limitations with that particular approach. Then we get into the very large field of probability-based sampling methods. Okay, and I'm not going to go through all of these because we're going to go through most of them in detail now anyway, but you could have just a very random sample approach, you could have a systematic point-based approach, you could stratify your sample. There's lots and lots of different approaches, and the challenge here is not just to randomly pick one, it's to recognize how the choice of one will actually affect your results and make a decision based on that. And I think that that's really hard. If my task in this whole module is to get you to think critically about statistics, unfortunately, how you understand these processes, it takes a long time to pick them up, and you need to get experience of working with them. So if you're interested in doing this type of work in the future, this is why it's so important that you do internships over the summer, or why you try to get involved in research at an early stage if that's the type of thing that you want to do in the future, because it just gives you more exposure to all of these different methods, and really it's only through that exposure that you actually pick up the information, that kind of real world information that you need to think critically about these in lots of depth. But this course really places you in a strong place in order to have the basics before you go on and do that. So hopefully you'll be able to understand the pros and cons of these different methods as we go through them now, and then hopefully you'll be able to apply them in a real world context at a later date. So simple random sampling, imagine that this is a 10 by 10 kilometre square grid that we've just put in the very centre of Fairfax, and then we just want to randomly select locations where we're going to sample the house price of the nearest building. So we could just select XY coordinates within that 10 by 10 kilometre square box. So the pros, it's very fast, it's simple, it's cheap. But there are cons, and that's essentially that the samples may cluster in one particular place, and that may mean that you avoid important locations. These decisions I have to make on a daily basis. So it's some work that we've been doing, planning cellular networks in many countries across Africa requires there to be a baseline understanding of the number of cellular assets that people use to connect to the internet or to make a phone call already in that location, and therefore you sometimes have to try to make a geographical estimate as to where they are, so a disaggregation, so that you have a baseline before you then decide what the cost may be, for example, for upgrading those cell sites or building new ones. But the problem with that random process is, well, do you just randomly distribute them, or do you try to geometrically distribute them to minimize the distance between each of them, or do you select some other type of method, maybe more of a stratified approach, so you're trying to put the actual existing cell sites, which are more likely to be in towns and villages, in those areas. And this is kind of a real-world example of how you may kind of approach these issues on a daily basis. So this may be sampling where you're trying to extract information, or you may have to think about the aspects of this process in terms of how you develop, in my case, an actual baseline for a disaggregation, essentially, for assets that are geospatially located on the ground. It's kind of the same thing, though, whether you're trying to approach these two different problems. So I think it's fairly common, if you're just doing this within the engineering literature, that you would simulate over these sampling frames as many times as possible using Monte Carlo analysis. So it kind of digs into the stochastic elements that I spoke about previously. This is kind of a more theory-driven approach to modeling physical processes, for example. You could create a computer simulation that randomly samples, and because just doing it once may introduce a lot of bias, as I'm demonstrating here, you may want to just sample them 1,000 times or 10,000 times. And then the actual error that you have when your sample starts to reduce, and you get a full distribution of what the outcomes may be. So again, this is getting into the philosophy of science and why you choose different approaches. Let's just assume that we're just trying to randomly sample house prices in Fairfax City. So before we had problems with clustering, maybe if we just randomly selected locations. What about systematic sampling? So this is where we have a regular sampling interval. It's really easy done. If we had this this tile again and it was 10 by 10 square kilometers, then maybe we could just introduce a sampling point at every 100 by 100 meter interval. And you might end up with something that looks a little bit like this, essentially. So it's very easy to implement. I could write some code which would basically produce this in about 20 minutes, and then it would give us the locations for which we then need to go off and sample. Obviously, there are cons, like any issue that we might occur. There are cons for any particular method that we might use. So we might actually miss important individuals that are necessary for us to actually include in our sample. So we might be actually missing some important points that fall between these sampling points that we've defined, okay, on a regular basis. Stratified sampling. So this is kind of moving towards what I would say is the gold standard for how we want to be doing our probability-based sampling. Okay, so we look at the population. So maybe we want to look at the population of the United States. Then we're going to want to stratify the population. And maybe we want to stratify that population down based on those demographic or economic characteristics, the socioeconomic characteristics, which really have a large influence on people's opportunities or how people live their lives. So for example, we may want to stratify that population based on age, so we have different demographic groups. We may want to stratify people based on income, gender, race. These are all hugely important issues which we need to take into account when we want to actually sample individuals. Okay, so here's an example based on a physical geography case where maybe you have two different types of soil types. Maybe you have one area that's a wetland and one area that's not a wetland, and then essentially what you want to do is to sample those points using either a proportional or a disproportional stratified point sampling approach. Okay. So essentially from those two examples I've given you, one based on demography, one based on physical geography, this approach is more representative and it helps to reduce the bias that's present within your sampling approach. Okay. The cons are obviously that it's more complex for you to actually implement, unfortunately. But I mean, this is just a fairly standard way that you would go about carrying out your sampling. I wouldn't personally opt for the other examples. I'd go straight to this one. It's a sunk cost. It's a cost which you just have to get over in order to do good research. Okay. Cluster sampling. So this is kind of handy. For example, if you want to kind of gain some of the benefits of both of these previous examples. So maybe we could divide the entire area into subgroups. So we spoke about this previously. When we're focusing on the systematic sampling, maybe we break the area that we want to sample down again. So maybe we do that on a 10 by 10 kilometers square area, and then these are 100 by 100 meter boxes, for example. And then we want to go into them, and then we want to sample lots of different buildings within each one of these, and then maybe we want to sample just 10 of the overall potential number of boxes that we could have. So yes, this can decrease costs and can help us get a large sample, but then there are also some cons with this approach. So if you're sampling neighborhoods, maybe this is kind of a good and a bad thing to do. Maybe providing your boxes fall on different socioeconomic styled neighborhoods, then that's fine. But if you end up only choosing a few boxes and they're all on similar neighborhoods, and then you go into them and you pull out lots of individual samples, you're not really overcoming the bias that might be present within that approach. So you just need to be aware that you could be introducing systematic bias. Hybrid sampling, so this is arguably better in the sense that you hear in this example actually using stratified systematic sampling based approach. So you draw up the grid system rather than focusing on a clustering approach within just a few cells. What you're doing is you're picking a random point across the entire sample area. If I was going to go about measuring house prices, and this was Fairfax, then this would probably be it would be an okay way to go. You'd have to make a decision about how big those tiles were going to be, but I think this would be a reasonably strong way to defend how you do that, given the fact that you've got uneven spatial processes beneath this grid. At least then when you do this, you would get a distribution of house prices, then you'd be able to take an average. And I suspect that that would be probably okay at trying to pick an average house price for the city if we took this approach. There are still issues, as I've explained here, just about how you actually determine the parameters for sampling, like the size of the tiles. Okay, great. Well, this is the 6th lecture. This is the end of it now. So hopefully you're all busy doing the revision for the ungraded tests and then also the midterm exam. So next week we'll get on to the 7th lecture where we start on some of those inferential tests, and we'll actually have another laboratory session next week. So this week we don't have one because you're all revising. Hopefully everything's going okay. Let me know if you've got any further queries, and I hope you enjoyed this content, and I'll see you all soon. Goodbye.